Hello, my name is Rashad Gafali and I'm a 9th grade student that has made a chemistry project. My supervisor is Ismail Sedek and we together have thought of a project that can be used for a lot of things. We have created an effective and inexpensive pump that shall be used to combat a specific problem. In many countries, one of the biggest problems is that not all fields are able to be irrigated. So according to combat this problem, we have developed an ingenious pump that uses the principle of air pressure to create that matter flows to the area of the lowest air pressure. We shall be creating a chamber of low air pressure that shall pull matter towards itself, and in our case, water. But we also have to think about the sources of energy. So we have thought of a pump that shall not use neither electricity or other infinite sources of energy, and it does not have that many problems. We developed a pump that shall combat these problems. How shall we make a low air pressure chamber? We shall be using a common element that's called urea. It's mostly used in agriculture, but is present in many places. One of the places that urea is present in is even in our urine. So according to how will urea be effective in creating a low air pressure chamber? Well, when urea decomposes, when it has been heated enough, it decomposes into ammonia, gaseous ammonia. When the gaseous ammonia fills the chamber, it shall create a low air pressure chamber. But there's also the thing is that ammonia is also a good source of nitrogen. And I shall explain why I told ammonia holds a good amount of nitrogen. And how shall we heat this urea into decomposition? We shall use a parabolic mirror that shall focus the sun's rays into a specific point. In a simplified version, we shall use solar energy. The following equation indicates the process of urea changing into ammonia. So in the simplified version, we have designed a pump that successfully transports water from its source to a desired area, and by using solar energy. So our hypothesis or idea on how we thought this would work. We thought that if we could make a chamber with low air pressure, we could use the process of suction to pull water from a specified source. When this water filled the container, we could direct it to a specified area. So in the simplified version, this is our diagram of it. This is our solar parabolic mirror, our container, our water source, our directory water, and our containers. So then how did we build it? I shall tell you about how we constructed this thing. Our procedure, well, we took two containers and connected them with a pipe with a tap. I shall tell you the importance of a tap later. We also connected 3 more taps to another container, which I shall name container number 2. Why do we need these 3 tubes with taps? We need these 3 tubes with taps for 3 reasons. One of these tubes shall be connected to a water source, another shall be connected to the area we want to direct our water to, and one shall be used to regulate the atmosphere inside the container. Why do we need to regulate it, you ask? I shall explain it now, but after the operation phase. But for now, we also add our solar parabolic mirror in a certain position, so the solar rays are focused to its focal point, aka the container number 1's bottom. Now our operation phase. We placed 5 grams of urea into container number 1 and started heating it with our parabolic mirror. As the urea started decomposing, we opened the tap on the first tap, connecting the 2 containers. Then we opened the regulatory tap. Why do we need to open the regulatory tap, you ask? Well, the thing is, the ammonia needs to push out whatever air was inside the 2 containers at that time. After the ammonia is sufficiently pushed out all the air and only ammonia exists inside these 2 containers, we close the regulatory tap. Then we open the water source tap. Then, as we see, that the suction process shall start. As the suction process started, it shall start filling the container number 2. For container number 2, we used a 500 milliliter flask for it. According to this flask, we added a limit on top of it for 400 milliliters. Why we did this, you ask? Because we do not want water to get into container number 1. Why? Because if water entered container number 1, we wouldn't be able to direct it to whatever source we wanted it to. As water fill reached the limit, we closed the water source tap and also closed the container number 1's tap. Because if we didn't close container number 1's tap, the water may enter container number 1 since suction still continues. As we now have a sufficient amount of water in container number 2, we open the directory tap. Now we open the directory tap, the water flows to whichever source we want it to, specifically in our problem, fields. Now, this is our diagram, the simplified version of how I explained it. Now our results, our data, we search on it. Since we don't have that much data because we simply constructed a manual system, a manual project, but we still have a little bit of data. We need to find the focal point of the parabolic mirror to focus it to container number 1's bottom. We found out that it was 75 centimeters inside the parabolic mirror. Then we also found out how much ammonia mixed inside, mixed with the water. Now why? Because as you remember, I told that ammonia has a high concentration of nitrogen, and nitrogen promotes plant growth. So if we know how much ammonia mixed with the water, we can know how much the plant grows. So we use 5 grams of urea, and theoretically, according to the equation, it will yield 2.83 grams of ammonia. Though to find the actual amount, because when we regulated it, some amounts of ammonia could escape through that too. So when we weighed the container number 2 and empty, it weighed about 183.84 grams. But then we weighed it with the condensed ammonia, so we haven't opened the water source tap. We weighed it in that, and it weighed 184.60 grams. So according to this, we found that we have 0.76 grams of ammonia mixed in with our water. Then according to this, it means that we had 0.76 grams of ammonia mixed with 400 amounts of milliliters of water. But then there's another thing that we researched, because for irrigation, the acidity of the water is important. So we checked how much acidic the ammonia affected the water. So we need to have an optimum pH level to prevent basic soil from appearing in the water. So we opened container number 2's cap and waited for the ammonia to evaporate from the water. In the first 30 minutes after we opened it, we found that the pH level with our pH meter, it was 8.7 acidity. The next 30 minutes, now 1 hour has passed, 8.2 acidity. And after 30 minutes has passed, we found out 7.5 pH acidity. So our average pH level in 1 hour and a half is 7.8 acidity. This we found out is the neutral pH level for irrigation. Now, in conclusion, we were able to make a system that was able to transport water from a source with the ability of suction. It didn't use any finite resources, it only used solar energy and a little bit of urea. Urea is also very cheap, and it also appears in our urine, it can be extracted from it. So we can find a lot of it, and it cannot be considered too much finite. According to this pump, in conclusion, it can be used in villages that are deficient of electricity, in countries that are absolutely poor, that can improve their agriculture, and even more so. In the future, we have planned to compare our ammonia water with fertilizer, because in the end, we didn't fully understand how much it is effective. We want to test it out, how our ammonia water compares with fertilizer. In our basic idea for this future project is we shall test 3 plants, one with fertilizer, one without fertilizer, and one with our ammonia water. So we made a pump that actually finished it. that was able to transport water. I thank you for listening. I hope I was able to explain it to your satisfaction.